In object-oriented programming, a class is an extensible program code template for creating objects, providing initial values for state and implementations of behavior. In many languages, the class name is used as the name for the class, the name for the default constructor of the class, and as the type of objects generated by instantiating the class. These distinct concepts are easily conflated. When an object is created by a constructor of the class, the resulting object is called an instance of the class, and the member variables specific to the object are called instance variables, to contrast with the class variables shared across the class. In some languages, classes are only a compile-time feature, while in other languages classes are first-class citizens, and are generally themselves objects. In these languages, a class that creates classes is called a metaclass. Class versus type. In casual use, people often refer to the class of an object, but narrowly speaking, objects have type. The interface, namely the types of member variables, the signatures of member functions, and properties these satisfy. At the same time, a class has an implementation, and can create objects of a given type, with a given implementation. In the terms of type theory, a class is an implementation, a concrete data structure and collection of subroutines, while a type is an interface. Different classes can produce objects of the same type. For example, the type stack might be implemented with two classes, small stack and scalable stack. Similarly, a given class may have several different constructors. Types generally represent nouns, such as a person, place or thing, or something nominalized, and a class represents an implementation of these. For example, a banana type might represent the properties and functionality of bananas in general, while the ABC banana and Zeiss banana classes would represent ways of producing bananas. The ABC banana class could then produce particular bananas. Instances of the ABC banana class would be objects of type banana. Often only a single implementation of a type is given, in which case the class name is often identical with the type name. Design and implementation. Classes are composed from structural and behavioral constituents. Programming languages that include classes as a programming construct offer support for various class-related features, and the syntax required to use these features varies greatly from one programming language to another. Structure. A class contains data field descriptions. These are usually field types and names that will be associated with state variables at program runtime. These state variables either belong to the class or specific instances of the class. In most languages, the structure defined by the class determines the layout of the memory used by its instances. Other implementations are possible. For example, objects in Python use associative key-value containers. Some programming languages support specification of invariants as part of the definition of the class, and enforce them through the type system. Encapsulation of state is necessary for being able to enforce the invariants of the class. Behavior. The behavior of class or its instances is defined using methods. Methods are subroutines with the ability to operate on objects or classes. These operations may alter the state of an object or simply provide ways of accessing it. Many kinds of methods exist, but support for them varies across languages. Some types of methods are created and called by programmer code, while other special methods, such as constructors, destructors, and conversion operators, are created and called by compiler-generated code. A language may also allow the programmer to define and call these special methods. The concept of class interface. Every class implements an interface by providing structure and behavior. Structure consists of data and state, and behavior consists of code that specifies how methods are implemented. There is a distinction between the definition of an interface and the implementation of that interface. However, this line is blurred in many programming languages because class declarations both define and implement an interface. Some languages, however, provide features that separate interface and implementation. For example, an abstract class can define an interface without providing implementation. Languages that support class inheritance also allow classes to inherit interfaces from the classes that they are derived from. In languages that support access specifiers, the interface of a class is considered to be the set of public members of the class, including both methods and attributes. Any private members or internal data structures are not intended to be depended on by external code and thus are not part of the interface. Object-oriented programming methodology dictates that the operations of any interface of a class are to be independent of each other. It results in a layered design where clients of an interface use the methods declared in the interface. An interface places no requirements for clients to invoke the operations of one interface in any particular order. This approach has the benefit that client code can assume that the operations of an interface are available for use whenever the client has access to the object. Example: the buttons on the front of your television set are the interface between you and the electrical wiring on the other side of its plastic casing. You press the power button to toggle the television on and off. In this example, your particular television is the instance. Each method is represented by a button, and all the buttons together comprise the interface. In its most common form, an interface is a specification of a group of related methods without any associated implementation of the methods. A television set also has a myriad of attributes, such as size and whether it supports color, which together comprise its structure. A class represents the full description of a television, including its attributes and buttons. Getting the total number of televisions manufactured could be a static method of the television class. This method is clearly associated with the class, yet is outside the domain of each individual instance of the class. Another example would be a static method that finds a particular instance out of the set of all television objects. Member accessibility: the following is a common set of access specifiers. Private restricts the access to the class itself. Only methods that are part of the same class can access private members. Protected allows the class itself and all its subclasses to access the member. Public means that any code can access the member by its name. Although many object-oriented languages support the above access specifiers, their semantics may differ. Object-oriented design uses the access specifiers in conjunction with careful design of public method implementations to enforce class invariance constraints on the state of the objects. A common usage of access specifiers is to separate the internal data of a class from its interface. The internal structure is made private, while public access and methods can be used to inspect or alter such private data. Access specifiers do not necessarily control visibility, in that even private members may be visible to client external code. In some languages, an inaccessible but visible member may be referred to at runtime, but an attempt to use it by referring to the name of the member from client code will be prevented by the type checker. The various object-oriented programming languages enforce member accessibility and visibility to various degrees, and depending on the language's type system and compilation policies, enforced at either compile time or runtime. For example, the Java language does not allow client code that accesses the private data of a class to compile. In the C++ language, private methods are visible, but not accessible in the interface. However, they may be made invisible by explicitly declaring fully abstract classes that represent the interfaces of the class. Some languages feature other accessibility schemes. Instance versus class accessibility. Ruby supports instance private and instance protected access specifiers in lieu of class private and class protected, respectively. They differ in that they restrict access based on the instance itself, rather than the instance's class. Friend. C++ supports a mechanism where a function explicitly declared as a friend function of the class may access the members designated as private or protected. Path-based. Java supports restricting access to a member within a Java package, which is the logical path of the file. However, it is a common practice when extending a Java framework to implement classes in the same package as a framework class in order to access protected members. The source file may exist in a completely different location, and may be deployed to a different .jar file, yet still be in the same logical path as far as the JVM is concerned. Interclass relationships. In addition to the design of standalone classes, programming languages may support more advanced class design based upon relationships between classes. The interclass relationship design capabilities commonly provided are compositional and hierarchical. Compositional classes can be composed of other classes, thereby establishing a compositional relationship between the enclosing class and its embedded classes. Compositional relationship between classes is also commonly known as a has-a relationship. For example, a class car could be composed of and contain a class engine. Therefore, a car has an engine. One aspect of composition is containment, which is the enclosure of component instances by the instance that has them. If an enclosing object contains component instances by value, the components and their enclosing object have a similar lifetime. If the components are contained by reference, they may not have a similar lifetime. For example, in Objective-C 2.0, at interface gar, ends object at property ends string asterisk name at property engine asterisk engine at property ends array asterisk tires, at end this car class has an instance of ends string engine and ends array. Hierarchical classes can be derived from one or more existing classes, thereby establishing a hierarchical relationship between the derived from classes and the derived class. The relationship of the derived class to the derived from classes is commonly known as an is-a relationship. For example, a class button could be derived from a class control. Therefore, a button is a control. Structural and behavioral members of the parent classes are inherited by the child class. Derived classes can define additional structural members and behavioral members in addition to those that they inherit and are therefore specializations of their superclasses. Also, derived classes can override inherited methods if the language allows. Not all languages support multiple inheritance. For example, Java allows a class to implement multiple interfaces, but only inherit from one class. If multiple inheritance is allowed, the hierarchy is a directed acyclic graph, otherwise it is a tree. The hierarchy has classes as nodes and inheritance relationships as links. Classes in the same level are more likely to be associated than classes in different levels. The levels of this hierarchy are called layers or levels of abstraction. Example: at interface uResponder, ends object. At interface UIView, uResponder. At interface uScrollView, UIView. At interface uItableView, uScrollView. In this example, a uItableView is a uScrollView is a UIView is a uResponder is an ends object. Definitions of subclass. Conceptually, a superclass is a superset of its subclasses. For example, a common class hierarchy would involve graphic objects as a superclass of rectangle and ellipse, while square would be a subclass of rectangle. These are all subset relations in set theory as well, i.e., all squares are rectangles but not all rectangles are squares. A common conceptual error is to mistake a part of relation with a subclass. For example, a car and truck are both kinds of vehicles and it would be appropriate to model them as subclasses of a vehicle class. However, it would be an error to model the component parts of the car as subclass relations. For example, a car is composed of an engine and body, but it would not be appropriate to model engine or body as a subclass of car. In object-oriented modeling, these kinds of relations are typically modeled as object properties. In this example, the car class would have a property called parts. Parts would be typed to hold a collection of objects such as instances of body, engine, tires. Object modeling languages such as UML include capabilities to model various aspects of part of and other kinds of relations. Data such as the cardinality of the objects, constraints on input and output values, etc. This information can be utilized by developer tools to generate additional code beside the basic data definitions for the objects. Things such as error checking on get and set methods. One important question when modeling and implementing a system of object classes is whether a class can have one or more superclasses. In the real world with actual sets, it would be rare to find sets that didn't intersect with more than one other set. However, while some systems such as flavors and Clo provide a capability for more than one parent to do so at runtime, introduces complexity that many in the object-oriented community consider antithetical to the goals of using object classes in the first place. Understanding which class will be responsible for handling a message can get complex when dealing with more than one superclass. If used carelessly, this feature can introduce some of the same system complexity and ambiguity classes were designed to avoid. Most modern object-oriented languages such as Smalltalk and Java require single inheritance at runtime. For these languages, multiple inheritance may be useful for modeling but not for an implementation. However, semantic web application objects do have multiple superclasses. The volatility of the Internet requires this level of flexibility, and the technology standards such as the Web Ontology language are designed to support it. A similar issue is whether or not the class hierarchy can be modified at runtime. Languages such as Flavors, Clo, and Smalltalk all support this feature as part of their meta-object protocols. Since classes are themselves first-class objects, it is possible to have them dynamically alter their structure by sending them the appropriate messages. Other languages that focus more on strong typing such as Java and C++ do not allow the class hierarchy to be modified at runtime. Semantic web objects have the capability for runtime changes to classes. The rationale is similar to the justification for allowing multiple superclasses. That the Internet is so dynamic and flexible that dynamic changes to the hierarchy are required to manage this volatility. Orthogonality of the class concept and inheritance. Although class-based languages are commonly assumed to support inheritance, inheritance is not an intrinsic aspect of the concept of classes. Some languages, often referred to as object-based languages, support classes yet do not support inheritance. Examples of object-based languages include earlier versions of Visual Basic. Within object-oriented analysis, in object-oriented analysis and in UML, an association between two classes represents a collaboration between the classes or their corresponding instances. Associations have direction. For example, a bi-directional association between two classes indicates that both of the classes are aware of their relationship. Associations may be labeled according to their name or purpose. An association role is given end of an association and describes the role of the corresponding class. For example, a subscriber role describes the way instances of the class person participate in it, subscribes to association with the class magazine. Also, a magazine has the subscribed magazine role in the same association. Association role multiplicity describes how many instances correspond to each instance of the other class of the association. Common multiplicities are 0, 1, 1, 1, 1, asterisk, and 0, asterisk, where the asterisk specifies any number of instances.